Dear students, in this section we are going to discuss Bohr's atomic model. First we are going to discuss some important theoretical points, then we will learn the application of the concept through some selected illustrations. So let us first discuss Bohr's assumptions for hydrogen atom. The first point about the assumptions is electron moves in the circular orbit around the nucleus, which is positively charged under the influence of the attraction force of the nucleus, right. So this is the first point. You can observe here in this diagram, this is the nucleus. Nucleus is having the JE charge positive and R is the radius of the rotation of the electron. Electron is having the negative charge. That means required centripetal force is provided by the Coulomb attraction. That is equal to K ZE multiplication E divided by R square. Let us call this radius as Rn. Rn means radius of nth orbit. So this Coulomb force provide the required centripetal force, that is equal to mvn square divided by Rn. Let the equation number 1, right. And second point, only certain electron orbits are stable, right. And these are the orbit in which electron does not emit energy in the form of electromagnetic radiation. That means when electron is orbiting in these stable orbit, electron does not emit any radiation in the form of electromagnetic energy. Okay. That means the energy of the atom remain constant and classical mechanics can be used to describe the electron motion. That means there is energy constant equation we can apply, conservation of the energy equation is applied. That means we can use the classical mechanics to describe this type of the motion. And one quantum mechanics term is also used. The size of the alloyed electron orbit is determined by the condition imposed by the electron orbital angular momentum. This is justified by the quantum mechanics and this is equal to mvr equal to ns divided by 2 pi. If velocity of the electron orbiting in the nth orbit is vn and radius is rn, so here we can write me, that is the mass of the electron. This is the velocity of the electron orbiting in the nth orbit. Rn is the radius of nth orbit and that is equal to ns divided by 2 pi. And n can take any value 1, 2, 3. Let this equation number 2, right. And this point is justified only through the quantum mechanics. We cannot justify this point using the classical mechanics model. Okay. So let us write equation number 1 and equation number 2 this to the next page. This is equation number 1 and 2. We can observe here Rn and Vn, two constants, and we have the two equations. That means if we solve these two equations, we can find the value of radius of the rotation, that is the radius of the nth orbit, and velocity of the electron also in nth orbit. So from first and second equation, if we solve these two equations separately, we will get the value of Rn equal to this n square h square divided by 4 pi square me k. K is the Coulomb constant, that is equal to 1 divided by 4 pi epsilon naught. Z is the atomic number and E is the charge in electron, right. We can observe here this h is a constant, Planck constant, 4 pi r square is a constant value, me is also constant, k is also constant and E is also constant. We can write the constant value separately in the bracket like this value. This is n is a variable, that is n is the number of the orbit, z is also variable, depends on the atomic number, right. That means we can observe here this Rn is proportional to n square divided by z, right. And if we calculate this value after substituting the value of z, pi, me, k and e, we will get this relation, that is Rn equal to 5.29 into 10 to the power minus 11 meter, n square divided by z. We can write this term in the angstrom, and we can write here Rn equal to this 0.53 angstrom n square divided by z. N is equal to 1, 2, 3 and so on, right. Now we can write this Rn equal to n square divided by Rn is proportional to, more appropriate, this is proportional to n square divided by z, right. And if n equal to 1 and for the hydrogen atom z equal to 1, we can observe here the radius for n equal to 1 and z equal to 1, say this radius is r naught and this r naught equal to 0.53 angstrom, right. For the hydrogen atom we know z equal to 1. So, Rn equal to 0.53 angstrom and this value is called the Bohr's radius, right. And we know this is proportional to n square. That means for n equal to t2, the radius corresponding to rotation of the electron is 4 times. N equal to 3, this is 9 times. So, we can write this relation n equal to 1 if it is r naught. For n equal to 2, it is 4 times r naught. N equal to 3, it is 9 times r naught, right. This is called the Bohr's radius. It is advisable to remember this relation because every time it is not possible to calculate these values, because these values are always constant, it will be fixed quantity. So, it is better to remember this parameter, that is 0.53 n square divided by z. Okay. So, let us move to the value Vn, that is the velocity of the electron in nth orbit. And here also from equation number 1st and 2nd, we can find the value of V, and this value is equal to 2 pi k z E square divided by nh. And here we can observe 2 pi is constant, k is also constant, E square is also constant and h is also constant. That means we can write like this, that is 2 pi k E square divided by h z divided by n. That means velocity of the orbiting electron in nth orbit is directly proportional to z divided by n, right. This is for the velocity. Now we can find the kinetic energy. We know kinetic energy is half m v square, and which particle is rotating? Electron is rotating. That means if electron is rotating, we can write the kinetic energy as half m e v square, and we have calculated the value of v. So, we can write the kinetic energy half mv square as, now we can substitute this value, this, right. We can calculate this, this is equal to 4 pi square divided by 2, it is again 2 pi s square, 2 pi square k square, this is m, and multiplication e to the power 4 here, and here is h square and n square also in denominator. So, this is the value, and here we can observe this 2 pi square k square m and e to the power 4 is constant, and this h is also constant, h square will be also constant. So, we can write k equal to this one, this is a constant value. Here we can observe this k is directly proportional to z square divided by n square, right. This is the kinetic energy. Kinetic energy is inversely proportional to n square for a given value of z, and here we can say velocity of orbiting electron is inversely proportional to n for given value of z, and for the radius we can observe radius is directly proportional to n square for given value of z. Okay. So, these are the important findings about the kinetic energy, velocity and radius. Okay. Now, come to calculation of the potential energy term. We know electrons are having the negative charge and they are orbiting around the positively charged nucleus, which is having the charge plus ZE. Electron is having minus E charge. The separation between the positive charge and negative charge is Rn. That means we can express the potential energy using the electrostatic formula for the potential energy. If two charged particles are having the separation r, we can express the potential energy as k q1 q2 divided by small r. This formula should be used with the proper sign of the charge. So, one charge here is positive, second charge is negative. So, here we can write u equal to minus k multiplication ZEE divided by R. That means minus k ZE square divided by R. This is the potential energy of the electron and nucleus system, right. This is negative. Negative potential energy always represent the bound state. Now, we can substitute the value of R we have calculated in the previous slide here. You can observe. So, if we substitute this value here, we will get this value of the potential energy. This is the value of R. R value we have substituted. Here also we can segregate the constant term separately. So, let us solve this expression. And finally, after segregation constant value, first this one, this value is a constant value 4 pi square k square m e to the power 4 divided by h square z square divided by n square. And here we can compare this potential energy relation with the kinetic energy. Here you can observe kinetic energy is 2 pi square k square m e to the power 4 divided by h square, and here this is 4. That means this potential energy is minus 2 times the kinetic energy, this term. So, here we can write u equal to minus 2k, right. And now come to the total energy. Total energy is nothing but it is the summation of the kinetic energy and potential energy. So, here we can write total energy of the system equal to k plus u, right. And k we have calculated here, this one, and u we have calculated here. Or here we can do one thing, we can substitute the value of u in term of k. So, this is k plus minus 2k, right, and this is equal to minus k. So, this is very important finding, that is total energy of the system of electron and nucleus is equal to minus k times minus k kinetic energy, right. You can say E equal to minus k. That is the magnitude of the total energy is equal to the kinetic energy, and if we multiply with minus 1, we will get the total energy of the system. That is the total energy of the atom, right. So, we can write now this relation. You can observe here this is the kinetic energy, and here we multiplied this relation with the minus 1. So, this is the relation, and here also you can observe here 2 pi square k square m e to the power 4 h square is a constant, and if we calculate this value is equal to minus 13.6 z square divided by n square electron volt, right. And for n equal to 1 and for the hydrogen atom z equal to 1, we can find the energy corresponding to the hydrogen atom. If n equal to 1, we say the atom is at the ground state. So, for n equal to 1 and z equal to 1, we can write E equal to minus 13.6, right. This is the energy corresponding to the ground state. So, we can say minus 13.6 is the total energy of the electron in the ground state of the hydrogen atom. Okay. So, we got the total energy relation. So, this is the total energy of the hydrogen atom or hydrogen like atom. For hydrogen atom Z equal to 1, for hydrogen like atom Z equal to 2, 3, 4, 5 etc. And for n equal to 1 means ground state, n equal to 2, 3, 4, 5 means excited energy state. Okay. And we know electron always rotate in atom in certain stable orbits only, right. And this electron can jump between the quantized energy level by emitting or absorbing the light, or you can say absorbing the radiation or photon energy, you can say more appropriate. Suppose one atom where the electron is at the ground state like this, and here photon energy or radiation energy is incident on this atom. If this energy is just sufficient for transit the electron from n equal to 1 to n equal to 2, then only this atom can absorb this energy. If this energy of the radiation is less than the difference of this energy, that is the difference of the energy of these two cells, the energy cannot be absorbed by the atom. That means, suppose this energy is just sufficient so that this electron can move from this level to this level. That means, the electron will move from lower energy level to higher energy level, and this type of the process is called the atomic excitation, and this will happen like this. This is the initial state, this is the final state. But this final state is not stable, because electron always have its own energy, that is the energy is defined by the quantum mechanics. And now what will happen? This electron at the higher energy state will return to its original level. This process is called the D excitation, and this D excitation is occur by emitting the photon energy like this. You can observe here, this an electron at the higher energy level will come to its original state by emitting the photon, and this is the process of atomic D excitation. This will be like this, from higher to lower. That means, electron in any atom can move from lower to higher and higher to lower energy level. Okay, and we can find the energy associated with the D excitation and excitation also. Suppose let us consider the atomic D excitation first, right? You can observe this photon is emitted when electron drop from larger a higher energy orbit to a smaller or lower energy orbit. That is the process of D excitation. Let us calculate this energy, and we know the energy of an electron, or you can say energy of an atom corresponding to nth orbit, is given by minus 13.6 Z square divided by n square in electron volt. Suppose electron was initially at the higher energy level and it is returning back to original level. So, here we can write for higher energy level, say it is E2 equal to minus 13.6 Z square divided by N2 square, and lower energy level, say it is corresponding to N1. So, we can write E1 equal to minus 13.6 Z square divided by N1 square, and let us write this energy is equal to delta E, right? And we know this delta E is emitted in the form of photon, and photon energy is nothing but hf or h nu. That's the h is a Planck constant and nu or f is a frequency. So, we can write electron jump from the higher energy to lower energy level, and this is equal to difference in energy related to the photon, that is hf. Okay. So, hf equal to E2 minus E1, and this is equal to difference which we have discussed. It is always in electron volt. Okay. We can find the wavelength also. We know we can write f equal to, this f is the frequency, and here we can write SC divided by lambda, and this is value is equal to 13.6 Z square, and this is equal to 1 divided by N1 square minus 1 divided by N2 square, and this is an electron volt. And for calculating this value, we can write 1 upon lambda. We are interested to calculate this value, this is lambda, 1 upon lambda equal to 13.6 Z square divided by SC, and this is equal to 1 divided by N1 square minus 1 divided by N2 square. And we know this SC is a fixed value, h is a Planck constant, c is the velocity of the light, and z is a value for any hydrogen like atom, right? So, we need not to calculate this value, that is 13.6 divided by SC always, and this value have a fixed result, and this is called the Rydberg constant. So, here we can write the wavelength of the emitted radiation is equal to 1 upon lambda equal to r infinite z square multiplication 1 divided by N1 square minus 1 divided by N2 square. and this is a fixed quantity, this is a constant, and this constant is called the Rydberg constant, right, and this is having the numerical value equal to 1.097 into 10 to the power 7 meter to the power minus 1, and this special value 1 upon lambda is called the wave number. Okay. So, this is the total energy of the transition of the electron from higher level to lower level in the form of radiation, and this is the wave number of the radiation or wave number of the photon emitted. And one thing is very important about the emission. When we pass this radiation emitted by the atom due to transition of the electron from higher level to lower level through a prism, because we know when we pass the light through prism we get the spectrum, and here we pass the radiation through prism, we will again get the spectrum, right, and this spectrum is called the emission spectrum because we are getting due to the emission of the photon through atom. And this emission spectrum we observe certain lines, certain discrete lines, and these lines are called the spectral lines, and number of these spectral lines depends on the excited state and value of Z. So, let us now find the way to calculate the number of the spectral line due to transition of the electron from n equal to n to n equal to 1. Okay. And now we know the number of the spectral lines emitted when electron jump from excited level to lower level. Suppose this excited level is n equal to n, we can say nth level to ground level transition is happening. From n equal to n to n equal to 1, let us consider the number of the possibilities through which the electron can move. It can move from n equal to n equal to 1, from n to n minus 2, from n to n minus 3, and so on. We can say n to 3, n to 2, n to 1. That means these are the possible ways. That is from n to n minus 1, n to n minus 2, n to n minus 3, n to 3, n to 2, or finally n to 1. These are the possibilities while motion of the electron from excited level to ground level. Why we are considering? Because sample of the gas may have many atoms, and in certain atom the excitation, D excitation from n equal to 1, and there may be possibility for getting the radiation corresponding to n equal to n equal to 1. If we count these number of the possibilities, these are n minus 1 possibilities, that is n minus 1 transitions. Now, let us find the number of the possibilities when electron start moving from n equal to n minus 1, that is nth level, to n equal to 1, that is the ground level. Number of the possibilities will be, in place of n we can substitute n minus 1, here will be n minus 2, here n minus 1, here will be n minus 3, and like this, and finally n minus 1 to 1. And if we count here, there will be n minus 2 transitions, right. Similarly, now let us consider from n minus 2th level to n equal to 1 or ground level. So, here what we will do? We will substitute in place of n minus 2. So, transitions here will be n minus 2 to n minus 3, n minus 2 to n minus 4, and here from n minus 2 to 1. And if we count here, there will be n minus 3 transitions. And similarly, if we keep on doing like this, finally we will reach to n equal to 2 level. From n equal to 2 to n equal to 1, there is only one possibility. That means only one transition is possible. If we add these number of the transition, that is 1, 2, 3, n minus 3 plus n minus 2 plus n minus 1. So, let us add number of the possibilities now. This is 1 plus 2 plus 3 plus n minus 2 and n minus 1 finally, because final was n minus 1 here. And we can observe this is the arithmetic progression, and the summation of the arithmetical progression, we have the simple formula, and this formula is equal to n multiplication n minus 1 divided by 2. So, this is the final formula we can use for counting the number of the spectral lines. Suppose electron initially is at n equal to 4, and we want to calculate, or we want to find the number of the spectral line. We write here in place of n, that is 4, and here is 4 multiplication 4 minus 1, that is 3 divided by 2. That means we will have 4 multiplication 3 divided by 2, that is equal to 6. That is the number of the transition, or number of the spectral lines will be 6. So, this is the way to find the number of the spectral line in the emission spectra. So, up to this point, we learn few important theoretical points. Now, we are going to move to the illustration section. In that section, we are going to take few important illustrations through which we are going to learn the application of the concept. So, let us move to the first illustration. In this illustration, it is given the potential energy of electron and proton at separation small r, given by capital U equal to k log r, where k is a constant. For such hypothetical hydrogen atom, calculate the radius of nth Bohr's orbit and energy level. Right? First of all, let us analyze the situation. What is the situation? Really, here it is. You are given U equal to k log r. K is a constant, and this log is natural log r, right? This is the potential energy relation between the electron and proton at separation small r. But while driving the formula for the nth Bohr's orbit and energy level, we use the relation, that is capital U equal to k ZE multiplication minus E divided by small r, that is equal to k minus k ZE square divided by small r. And we calculated the force between the electron and nucleus, that is equal to k ZE square divided by r square, and we equated this force equal to mv square divided by small r. That was Coulomb force was responsible for providing the centripetal force for orbiting the electron in the atom. But here the potential energy is given by the different formula, because it is the hypothetical hydrogen atom. That means we cannot use the Coulomb formula for calculating the force, and this force cannot be equated with the centripetal force. So, what we need to do? We need to calculate the force for this type of the potential energy. This can be calculated by differentiating this relation with respect to r with the negative sign. We know the force in any conservative field is given by minus du by dr. So, let us calculate the force F equal to minus du by dr, and u equal to k log r, and differentiation of this log, that is a natural log r, equal to 1 upon r. So, this force is equal to minus k divided by small r, right. This is the force between the electron and nucleus, and we know this force is responsible for providing the required centripetal force. That means we can equate the magnitude of this force with mv square divided by small r. Let this equation is equation number 1. Now, let us move to the second rule of the Bohr's quantized theory or Bohr's atomic theory, and we know the angular momentum of the orbiting electron can be given by mvr equal to ns divided by 2 pi, right. Let us call this equation as equation number 2. Let us write equation number 1 and equation number 2 to the next page. And here we can observe, we have the two unknowns, that is v and r, and we have the two equations. That means these two unknowns can be calculated. V, that is the speed of the electron, we can calculate for finding the kinetic energy of the orbiting electron. And radius of the nth Bohr orbit we can calculate if we calculate the value of small r. So, let us do one thing. Let us first calculate the value of small r. So, we can do one thing, we can square equation number 2 and divide this equation square with first equation. This will be like this. Here we can observe this v square and v square will get cancelled and this r and r will also get cancelled, right? And here will be m square and denominator is m. So, only m will be left, and after rearranging, after solving, we will get the relation, that is m r square, this is m r square, this is equal to n square h square divided by 4 pi square and k. This is the relation. That means we can find the value of r square, and this r square equal to n square h square divided by 4 pi square k multiplication m. Now we can find the radius of nth Bohr orbit by under root of this value, right? This is r value. This is the radius of Bohr's nth orbit, right? Now let us find the kinetic energy. We know before calculating the kinetic energy, we can calculate total energy. We can write the total energy term. We know total energy is equal to summation of the kinetic energy and potential energy, right? So, let us write kinetic energy and potential energy. And potential energy relation we have given, that is equal to k log r, right? And we know the kinetic energy here, this is mv square equal to k. So, we can write 1 by 2 mv square equal to k by 2. So, we got the kinetic energy. So, here we can write this kinetic energy is equal to k by 2 and potential energy equal to k log r. Now, we can substitute the value of r. This relation of r is in term of n, that means this total energy is in relation of n, that is the energy level, that is the energy corresponding to nth level. So, this is the total energy corresponding to this hypothetical hydrogen atom. Now, let us move to the next illustration. In this illustration, we need to find the angular momentum of an electron in Bohr's hydrogen atom whose energy is minus 13.6 electron volt, right? What is being asked? Angular momentum. We know electron orbit around the nucleus in the circular orbit. For calculating the angular momentum of any point object around circular path, or you can say circular orbit, we can use the formula mvr. But in this formula, in this problem, we are not given the velocity, that is v, we are not given the value of a small r, that is the radius of rotation. That means we cannot calculate the angular momentum by using the formula mvr. That means we should use some different approach, and we know the quantization formula for the angular momentum that was given by the Bohr's, that is equal to mvr equal to ns divided by 2 pi, right? That means from left hand side expression we cannot calculate the angular momentum, we should use the right hand side expression, that is ns divided by 2 pi, okay? And here we given the total energy, and we have the relation for the total energy, that is equal to minus 13.6 z square divided by n square, and it is the hydrogen atom, that means z equal to 1, that means total energy equal to minus 13.6 divided by n square, right? So, we can write this relation, that is E equal to minus 13.6 divided by n square, and here total energy is given as minus 3.4 electron volt. Here minus minus will get cancelled, we can get the value of n square equal to 4, and that means n equal to 2. Now, we can substitute the value of n in this formula, that is 2s divided by 2 pi, and 2 and 2 will get cancelled, right? And here we get the result s divided by pi. This is the angular momentum corresponding to this energy, that is minus 13.6 electron volt. Okay. Now let us move to the next illustration. In this illustration, we need to find the ratio of the ionization energy of the Bohr's hydrogen atom and doubly ionized lithium ion, right, this one. And we know the total energy of hydrogen like atom. We have the formula, that is equal to minus 13.6 Z square divided by N square, and this energy is always in electron volt. So let us write this expression, this one, right. And we know that ionization energy is the energy required to eject the electron from n equal to 1 to n equal to infinite. That is, for removing the electron from ground state to out of the atom, that the minimum energy required is the ionization energy. That means we need to find the difference of the energy corresponding to n equal to infinite or n equal to 1. Right. So, we can write ionization energy equal to E 1 to infinite, right, that is equal to E infinite minus E 1. We know E infinite equal to 0, just move the electron outside the atom. So, we should write E infinite equal to 0 and E 1 equal to minus 13.6 Z square divided by 1 square. So, let us write this equal to 0 minus E 1. Now, we can write this relation, that is minus 13.6 Z square divided by 1 square, right. This one minus minus will be positive. This is the energy required. We can write now this is equal to 13.6 Z square electron volt, right. Now, we can say it is nothing but the magnitude of the energy at the ground state. We can say ionization energy is nothing but it is the magnitude of the energy of the atom at the ground state. This is the energy at the ground state. Now, we can find the ratio. We need to find the ratio of the ionization energy of the Bohr's hydrogen atom and doubly ionized lithium ion. We know this energy is proportional to Z square. So, here we can write E ionization for the hydrogen divided by E ionization for the lithium, that is equal to Z square for the hydrogen divided by Z square for the lithium. So, let us write this relation now, right, and we know Z equal to 1 for the hydrogen and for the lithium plus this value is 3. So, this is 1 divided by 3 square and this is 1 divided by 9. So, this is the required ratio. Now, let us move to the next illustration. In next illustration, we need to determine the minimum wavelength of photon that cause ionization of helium ion, right. And we know the total energy of hydrogen like atom. We can express the total energy with the formula minus 13.6 Z square divided by N square, this formula. And we also know the definition of the ionization energy. It is the energy required to eject the electron from n equal to 1 to n equal to infinite. That is the minimum energy required for removing the electron at ground state to out of the atom, right. This energy is the ionization energy. That means we can write ionization energy is equal to E infinite minus E 1, E infinite equal to 0. That means ionization energy equal to minus of E 1 and E 1 is a negative quantity. If we substitute n equal to 1, this is the negative quantity. That means the magnitude of the energy at the ground state is the ionization energy, right. Now, let us write the energy corresponding to the ground state. That means we need to substitute n equal to 1 in this expression. So, let us write n equal to 1 and here we need to calculate for helium ion. So, Z equal to 2. So, let us substitute n equal to 1 and Z equal to 2. Let us calculate E1, that is magnitude of E1. Let us calculate the magnitude here. So, it will be equal to 13.6 2 square divided by 1 square. right, and this value will be 13.6 multiplied by 4. This is equal to 54.4 electron volt. This is the magnitude of the energy at ground state for helium ion, right, this type of the helium ion. And we know the energy of the photon is given by Sc divided by lambda, and this energy is required is 54.4 electron volt. That means this energy, that the magnitude of E1 should be equal to Sc divided by lambda, right. To ionize the helium ion should require this much energy. That means E1 magnitude equal to E, that is equal to Sc divided by lambda. And we know this Sc is a fixed value, and we have the shortcut formula for calculating the wavelength. If we express the energy in electron volt and lambda in the angstrom, we can write this lambda equal to 12400 divided by E in electron volt. By this formula we can write. Now we can substitute the value of E, that is a 54.4. So it is equal to 12400 divided by 54.4. After calculation, this is equal to 228 angstrom. So this is the wavelength, that is the minimum wavelength required for ionization of the helium ion. Now let us move to the next problem. In next problem, you can observe there is energy level diagram for hydrogen like atom. You can observe for the ground state, that is n equal to 1, energy is 54.4 with a negative sign, and unit is electron volt, and n equal to 2, it is minus 13.6, and so on. In the first part of the question, it is asked find the value of Z, that is the atomic number. Second question, it is asked if initially atom is at ground state, then A question determine the excitation potential, and in the B part of the question determine the ionization potential. And third question, it is asked can it has absorbed the photon of 32 electron volt, and in the fourth question it is asked can it has absorbed photon of 54 electron volt. And the fifth part of the question, it is asked calculate the radius of the first Bohr orbit, and sixth question, it is asked find the kinetic energy and potential energy of an electron in first orbit. Okay, so let us move one by one. Let us make the energy level diagram, and let us first analyze the first part of the question to calculate the atomic number Z. So this is the question. Okay, you can observe here n equal to 1, energy is minus 54.4. These are the energy level. You know, these energy levels governed by the formula which is given by En equal to minus 13.6 Z square divided by n square electron volt, right. If we substitute the value of Z, that is the atomic number, and for value n equal to 1, 2, 3, 4 and so on, we get the value of En, and we know these values are value of En. Okay, but here energy level diagrams are given, and n is also given, and we need to find the value of Z. We can select here n equal to 1, this value minus 54.4. So here we can write n equal to 1, E1 equal to minus 54.4 electron volt. Okay, now we can substitute this value in this formula, and this n equal to 1, this is minus 54.4, that is equal to minus 13.6 Z square divided by 1 square. 1 square is nothing but n square. Okay, now let us solve for Z. Minus sign and minus sign will get cancelled, and here we can get the Z equal to under root 54.4 divided by 13.6, and this is a root 4, and root 4 is nothing, it is 2. That means the value of Z equal to 2, that is the atomic number is 2, that is helium. Okay, now let us move to the next part of the question. This is the next part. Question is if initially atom is at ground state, that means electron is at ground state, that is corresponding to n equal to 1. We need to find the first excitation potential. let us analyze the first part, that is the A part of the question. We know the first excitation energy is the energy required to excite the electron from this orbit, that is n equal to 1 to n equal to 2. That means for this type of the transition, right? And this is the first excitation energy for n equal to 1, this is n equal to 1 and this is n equal to 2, right? And we are given the value of n equal to 1 and we are also given n equal to 2. That means we can find here the excitation energy, that is the first excitation energy, that is equal to delta E12, that is again equal to E2 minus E1. So, let us write delta E12 equal to E2 minus E1 and that will be equal to minus 13.6 minus 54.4. Okay. Let us substitute this value. So, this is equal to, after solving, this will be equal to 40.8 electron volt. This is the energy required. And here we need to find the excitation potential, that is the first excitation potential. For calculating potential from energy given in electron volt, what we need to do? We should divide energy with E. If we divide this expression with E, this value will be equal to 40.8 volt. So, excitation potential for this required value is equal to 40.8 volt. This is the A part. Now, let us move to the B part, that is determine the ionization potential. Ionization potential is the energy required for eject the electron from ground state to n equal to infinite. That means to move the electron from ground state to out of the atom, that energy is the ionization energy. Okay, and you can say this energy, we know this energy is also the energy, that the magnitude of the energy at the ground state. So, directly we can say that will be equal to 54.4 electron volt, because unit is here electron volt. So, let us write this systematically. We know this ionization energy is the energy required to eject the electron from n equal to 1 to n equal to infinite. So, we can write delta E 1 to infinite, that is equal to E infinite minus E1. And we know this E infinite is nothing but 0 and E1 equal to minus 54.4. So, it is 0 minus 54.4, right, and this is numerically equal to energy at the ground state, that is a 54.4 electron volt. That means ionization potential, we need to calculate the ionization potential. This is the ionization energy. Here we need to do one thing, we need to divide this energy in electron volt with E. So, ionization potential here will be equal to 54.4 volt. So, this is the B part of the question. Now, let us move to the C part of the question. No, that is the third part. There was only A and B, two parts. So, let us move to the third part of the question. The question is, can it absorb a photon of energy 32 electron volt, right? Suppose electrons in this atom is at the ground state, it was given also, and it absorbs 32 electron volt. That means the energy of the electron will become minus 54.4 plus 32. So, let us absorb this energy to the atom at the ground state. So, this is equal to 54 plus minus 54.4 plus 32. This is equal to 22.4 with negative sign, this electron volt. You know, if electron absorb this much of the energy, final energy will become minus 22.4 electron volt. But we can observe the next energy state is minus 13.6. That means if it absorb energy, the energy state should be minus 22.4. But there is nothing, no this type of the energy level. That means this atom cannot absorb 32 electron volt of energy, right? Because this energy level or this energy is between n equal to 1 to n equal to 2, and we know intermediate states are not possible in the atom. because electron can present only in the well-defined orbits only. So, this cannot absorb, that is 32 electron volt cannot be absorbed by the atom. Now, move to the fourth part of the question. Can it absorb a photon of 54 electron volt, right? That means if electron is at the ground state, that means it is having energy 54.4 minus 54.4 electron volt. After absorbing this much of energy, energy of the electron will be positive, and at n equal to infinite, energy is 0. That means after getting this much of the energy, this electron will escape from the atom. That means the remaining energy, that is 56 minus 54.4, that means the remaining energy will be available for electron as a kinetic energy. This energy absorption is possible. So, this was the answer for the third part, and second part we have discussed. This answer is no, and fourth part answer is yes. By absorbing the photon of this energy, electron move out of the atom, and energy, because after this state energy is not quantized. That means remaining energy will available for the electron as a kinetic energy. Now, let us move to the fifth part of the question. Calculate the radius of the first Bohr orbit, and we have the formula for the radius of the cell. We know that is radius of the nth cell equal to minus 5.3 n square divided by z, right, this much. This is the in angstrom. And if for hydrogen atom we want to calculate the first Bohr orbit, what we will do? We will substitute z equal to 1 and n equal to 1, and first Bohr orbit for the hydrogen atom is 0.53 angstrom. And here we calculated the value of z, that is equal to 2, and here we need to calculate the Bohr orbit, that means for n equal to 1. That means in the formula we should substitute n equal to 1 and z equal to 2, right, and this value will be equal to R1 equal to 0.53 1 square divided by 2. This is equal to 0.265 angstrom, right, this much. This is the answer for the fifth part. Now, for the sixth part, we need to calculate the kinetic energy and potential energy of an electron in the first orbit, right. Now, we need to calculate the kinetic and potential energy for the first orbit, and we know the magnitude of the kinetic energy is equal to numerical value of total energy, and more appropriate we can write kinetic energy equal to minus of E, that is minus of the total energy. We know this formula, and we also know the formula for the potential energy, that is potential energy equal to twice the total energy. So, first of all, we can write kinetic energy equal to minus E and potential energy equal to twice of total energy, right. This potential is negative and total energy is also negative, and this is the negative value. That means this negative value multiplied by negative sign, this will be positive, that is kinetic energy is always positive. So, here we can write E value for n equal to 1 is 54.4. So, we can write here minus 54.4, if it is multiplied with the negative sign, this will be equal to 54.4 electron volt. So, this is the kinetic energy for the first orbit, right. Now, move to the second part of the question to calculate the potential energy. We know potential energy equal to twice the total energy, and total energy is minus 54.4. So, it is 2 multiplied by minus 54.4, and this will be equal to minus 108.8 electron volt. So, this is the potential energy. Okay. Now, let us move to the next illustration. Next illustration again related with the energy level diagram. This is the energy levels for hypothetical 1 electron atom, right. This is a hydrogen like atom again, and this is the energy level diagram, but it is a hypothetical atom, right. The question is first part of the question, it is asked, find the ionization potential of the atom, and in the second part of the question, find the excitation potential for state n equal to 3, and in the C part of the question, what is the minimum energy for the electron will have after interacting with the atom in the ground state if initial kinetic energy of the electron is, and first part this is 6 electron volt and second is 11 electron volt. Let us move to the first part of the question, that is the find the ionization potential of the atom. For calculating ionization potential, we need to find the ionization energy. And we know ionization energy is the energy required to eject the electron from the atom from ground state, that is from n equal to 1 to n equal to infinite, right? And here we know E for n equal to 1 is minus 15.6, and for n equal to infinite it is 0. So it is given, that is E1 equal to minus 15.6 electron volt, and E infinite, that is n equal to infinite, E value is 0 electron volt, right? And we know ionization energy equal to E infinite minus E1, that is the 0 minus 15.6 electron volt, and this numerical value is equal to 15.6 electron volt. That is magnitude of the energy at the ground state. We can directly say ionization energy is the energy, that the magnitude of the energy at the ground state. Now we can find the ionization potential. We should divide this quantity with the E. So this ionization potential is equal to 15.6 volt. So this is the A part, that the ionization potential we have calculated. Now let us move to the B part, that is the find the excitation potential for the state n equal to 3, right? For n equal to 3, that is energy required, energy related with the n equal to 3 is minus 3.08 electron volt. And we know excitation energy. For calculating excitation potential, again we need to find the excitation energy. Excitation energy for state n equal to 3 is the energy required for this transition, that is from n equal to 1 to n equal to 3. For this transition, this is n equal to 1 to n equal to 3. So energy required should be equal to E3 minus E1. So let us first calculate the excitation energy, that is E3 minus E1. So excitation energy is E3 minus E1, okay? And we know E3 equal to, we have calculated E3 equal to minus 3.08, and here this value is 15.6. So this is minus 3.08 and minus 15.6, and minus will be plus. So this value is equal to 15.6 minus 3.08. And this numerically it is equal to 12.52 electron volt. And for calculating the potential value, we should divide this quantity with E. So we can calculate excitation potential equal to E3 minus E1 divided by E, that is equal to 12.52 volt. So this is the B part of the question. Now let us move to the next part, that is the C part of the question. In C part of the question, it is asked what is the minimum energy that the electron will have after interacting with this atom in the ground state if the initial kinetic energy of the electron is 6 electron volt and second 11 electron volt, right? Let us first understand when an atom receives the energy for the excitation process. An atom can receive energy in the form of radiation, number 1, number 2 from collision, number 3 from heating. Only 3 processes can excite the electron in the atom, right? And if outer electron, you can say external electron is interacting with the atom, this electron will interact with the atom only if when it has energy equal to or greater than the energy required for the excitation of the energy for the second cell. That is, if electron is having energy greater than this energy, that is energy required for transition from n equal to 1 to n equal to 2, then only this atom, this hypothetical atom will interact with the electron. That means, first of all, let us calculate the excitation energy for n equal to 2 state. That means that will be equal to E2 minus E1, delta E equal to E2 minus E1, and E2 equal to minus 5.3 electron volt and E1 equal to minus 15.6 electron volt. That is minus 5.3 minus 15.6 electron volt, that will be equal to 10.3 electron volt, right. That means, if any radiation or atom, you can say any radiation or external electron have energy of this value or greater than this value, then only interaction is possible. And here you can observe this electron is having initial energy equal to 6 electron volt, which is less than the energy for excitation for n equal to 1 to n equal to 2. That means, this energy, that is excitation energy for the second cell, is more than 6 electron volt. That means, electron having the kinetic energy that is equal to 6 electron volt is not going to interact with the atom. That means, the energy of the electron will remain same as previous, because it is not going to interact with the atom. Okay. Now, move to the second part of the question. In second part of the question, energy is 11 electron volt, and we have calculated energy for the excitation energy for the second cell is 10.3 electron volt, and we have 11 electron volt. That means, this electron can interact with the atom, right, because energy having this much value, that is 11 electron volt. That means, this electron is going to interact with the atom, and what will happen? This much of the energy, that is 10.3 electron volt energy, will utilize for this transition, and remaining part of the energy, that is 11 electron volt minus 10.3 electron volt, that is equal to 0.7 electron volt energy, will remain as a kinetic energy of the electron, right. That means, energy of the electron after interaction will be 11 minus 10.3, that is equal to 0.7 electron volt. So, we can say the energy after interaction, that is the kinetic energy after interaction, should be equal to 0.7 electron volt. Okay.